And then 2011, it wasn't that exciting. But something happened in 2012. That was the most exciting year. That year, Jeff Hinton and his students participated in this challenge using convolutional neural network, and they reduced the error almost by half, and truly showed the power of deep learning algorithms. And so the participating algorithm in 2012 ImageNet challenge was called AlexNet. And the funny thing is, if you look at AlexNet, it's not that different from the Fukushima's neocognitron 32 years ago. But two major things happened between these two. One is that backpropagation happened. It's a principled, mathematically rigorous learning rule so that you don't have to ever use hand to tune parameters. And that was a major breakthrough theoretically. Another breakthrough was data. The recognition of data and the understanding of data driving these high capacity models, which eventually will have trillion parameters, but at that time was millions of parameters, was critical for setting off the deep learning, for this to work. And really, many people consider the year of 2012, the AlexNet algorithm that won the ImageNet challenge, the historical moment of the birth of or rebirth of modern AI, or the birth of deep learning revolution. And of course, the reason many of you are here is since then, we are in the era of deep learning explosion. If you look at computer vision's main annual research conference called CVPR, the number of papers have exploded, and archive paper has exploded, and many new algorithms since then have been invented to participate in the ImageNet challenge in the following years. We're going to study some of these algorithms, but the point is that some of these algorithms beyond AlexNet have had a profound impact in the progress of the field of computer vision and into the applications of computer vision. So a lot of things have happened, and we're going to cover some of these. Not only the field of computer vision made a major progress in creating algorithms to recognize everyday objects like cats and dogs and chairs, we also quickly, right after ImageNet challenge, the 2012 moment, we've got algorithms that can recognize much more complicated images, can retrieve images, or can do multiple object detections, can do image segmentation. These are all different tasks in visual recognition that you'll find yourself getting familiar with throughout this course, because vision is not just calling out cats and dogs. There's so much in the nuanced ability of visual recognition. And of course, vision is not just static images. So there are work in video classification, human activity recognition. I'm showing you this overview. You will learn some of these. These are all, you don't have to understand exactly what's going on here, but I want you to appreciate the variety of vision tasks. Medical imaging, those of you who come from a medical field, is whether it's radiology or pathology or even other aspects of medicine, is deeply visual, and this has a profound impact. Scientific discovery, even the seminal picture you probably remember of the first photography of black hole uses a lot of computer vision and computational photography techniques. Of course, applications in sustainability and the environment is also, computer vision contributed a lot of that. And We also have made a lot of progress in image captioning. Right after the ImageNet 2012 moment, this is actually work by Andre Kapathy. He was my student, his thesis work. Then we also worked on, relationship understanding. So not only visual intelligence is about seeing what's on the pixel, you can also see what's beyond pixels, including relationships of objects, and also style transfer. A lot of this work you will actually, Justin Johnson, who will come to guest lecture this course, will tell you all about his seminal work in style transfer. And of course, in generative AI eras, we get these really incredible results like, face generation. And, this is the very early days of image generation of DALL-E. I think this is the early DALL-E. Of course, now Midjourney and everything has gone beyond these avocado and peach chairs. But really, we are squarely in the most exciting modern era of AI explosion. The combination, the three converging forces of computation, algorithms, and data have taken this field just to a whole different level where we're now totally out of AI winter. I would say we're in an AI global warming period. And I don't see any of this slowing down. So, for both good and bad reasons. And also, just a word, because we are in the Silicon Valley. We're in the very building of Huang Building and NVIDIA lecture hall. So we cannot ignore also the progress of hardware and what that played. So here is just the flop per dollar graph for NVIDIA's GPUs. And before 2020, the progress was steady. But as soon as deep learning started to drive these GPUs and chips, you can just see the G-flops have just completely taken off. And, we're just, by any measure, we are in this accelerated curve of lots of compute as well as lots of AI. And these are just different graphs showing you conference attendance, startups, and enterprise applications in AI all across, not just computer vision, but also NLP and others have just exploded. Okay, so quickly, last but not the least, it's been exciting. There has been a lot of successes, but there is still a lot to be done in computer vision. So this problem is still not totally solved. And with great tools comes with great consequences as well, right? So, computer vision can do a lot of good, but it also can do harm. For example, human bias. Every single AI algorithm today, the large ones, are driven by data. And data is an artifact of human activities on Earth and in history. And a lot of the data carry our bias. And this gets carried in AI systems. We have seen a lot of face recognition algorithms having the same kind of bias that humans have. And we do have to really recognize that. We can also use AI to impact human lives, some for the good, think about medical imaging, but some are questionable. What if AI is solely behind deciding your job or deciding your financial loans? So, again, is it totally bad? Is it totally good? These are very complicated issues. This is also why I always get so excited when students from HNS or law school or education school or business school attend my class, because not all AI issues are engineering issues. We have a lot of human factors and societal issues to solve. I'm also particularly excited by AI's medicine and healthcare use, and this is something really dear to my heart, that Professor Deli and Zane, who are also co-instructors of this course, we three of us work on AI for aging population as well as patients, and to try to use computer vision to deliver care to people. So this is a good use. And also, even in terms of technology, human vision is remarkable. I want you to come out of not only today's class, but also this entire course to appreciate, despite how much computer vision can do, there's just so much more nuance, subtlety, richness, complexity, and also emotion in human vision. You know, look at these kids studying whatever that their curiosity lead them, or the humor in this image. There's still a lot more that computer vision cannot do. So I hope that continue to entice you to study computer vision. At this point, I'm gonna give the podium to Professor Deli to go over the rest of the class. Thank you.
Awesome. Thank you, Feifei. Great start of the quarter, and I hope my microphone is working right now. Okay, good. I'm seeing some nodding of heads. All right, so very excited to be here with you all, and I'm hoping that you will have a fun and challenging course with an amazing list of co-instructors that we have and great TAs. So in this class, we are going to cover a wide variety of topics around computer vision and use of deep learning in this space, categorized into 4 different topics. We'll start with deep learning basics. And let's start actually with a simple question of what is computer vision really? So at its core, it's about enabling machines to see and understand images. And basically, this is the most fundamental task in this space. In this space is image classification. You give the model an image, say, of a cat, and the model should output a label, cat. And that's it. But it's this deceptively simple task is the foundation for much of more complex applications, from self-driving to medical diagnosis and so on. So how do we teach a machine to do this? One of the simplest approaches is to use linear classification, as you can see in this slide. So imagine each of the images in our data set is shown with a dot in that space, and each axis shows some sort of feature which was driven from the image itself. Here we are showing a 2D space but, for simplicity, but the task of a linear classifier is to find the hyperplane or the linear function that separates these two, say, cats from dogs. But we all know that these linear models often go just only so far. They struggle when the data isn't cleanly separable with a straight line. So the question is, what's next? We'll get into the topics of how to model more complex patterns. And if we do so, we often face challenges of overfitting and underfitting, which are the topics we will cover in the early lectures of the class. And to strike the right balance, we use techniques like regularization to control model complexity and optimization to find the best fit parameters. So these are the nuts and bolts of deep learning and creating these models, training models that not only fit the data, but also generalizes to unseen and new data as well. And now comes the fun part, neural networks. We've been talking about them quite a lot. And what neural networks do, unlike the linear classifiers, they stack multiple layers of operations to model nonlinear functions to be able to either classify, to solve the same problem of image classification, and so on. These are the models powering everything from Google Photos, and now everybody's familiar with ChatGPT, ChatGPT's vision models, and so on. In this course, we will go deep into the details of how they work, how they are trained, and we will be looking into how to debugging and improving them. After looking at the deep learning basics, we will cover the topics of perceiving and understanding the visual world, which is a complex process that involves interpreting a vast array of visual information. And to do so, we often first define tasks that refer to specific challenges or problems. We aim to solve. Some of the examples are object detection, scene understanding, motion detection, and so on. And to solve these tasks, we use different models, which are computational and theoretical frameworks we develop to mimic or explain how our visual system accomplishes these tasks. One of the examples of these types of models is neural networks. So by aligning models and with tasks, we can create systems that can see and interpret the world around us. Speaking of tasks, let's go back to the topic of image classification, predicting a single label for an entire image. But we know that real-world computer vision is much richer than this, and let's walk through some of the tasks that go beyond classification. First, semantic segmentation, where we are not just labeling the object or the entire image as cat or tree or whatever. Here, we are looking for labels for every single pixel in the image. So every pixel is a grass, cat, tree, or sky, but we don't distinguish between individual objects. And next we have object detection, where we now want to not only say what is in the image, but also pinpoint the location. And that's why we create bounding boxes around the objects and associate them with specific labels. And finally, we have instance segmentation. We'll go into instance segmentation, which is the most granular of them all. It combines the ideas of detection and segmentation together, and every object instance gets its own mask. So these tasks require, much deeper understanding, special understanding in images, and they push the models to do more than just recognizing categories. The complexity doesn't stop with static images. Let's look at some temporal dimensions. So there's the task of video classification, as Feifei talked about, where we want to understand what's happening in the video. Is there someone running, jumping, or dancing? There is the topic of multimodal video understanding, which is combining vision and sound and other modalities. For example, in this example, the person is playing a vibraphone. To really understand what's happening here, we have to create a blend of visual features and audio features to be able to understand what's happening. And finally, there is the topic of visualization and understanding that we will be covering in this class, where we want to interpret what's being learned by the models and see an attention framework, attention map of what the model is attending to do a correct classification, and so on. And then we have models. Beyond tasks, we look into models, and the very first topic, let me introduce to you, that we'll be covering is convolutional neural networks, or CNNs. There are a number of operations. We will be going over the details in the class, starting from an image, a number of convolution, sampling, and fully connected operations, and finally creating the output. And beyond convolutional neural networks, we will study recurrent neural networks for sequential data and even newer architectures such as transformers and attention-based frameworks. So next we will be covering some large-scale distributed training topics, which is kind of new this quarter. I'm sure you've all heard about large language models, large vision models, and so on. And we will be briefly discussing how these models are actually trained. We know that data and data sets are expanding. Models and large models are becoming larger and larger. And in order to train such models, there are some strategies. For example, data parallelization, model parallelization that we'll cover in this class. But beyond that, there will be so many challenges, such as synchronization between these models and workers and so on, as well as several other aspects that we'll be covering in one of the lectures this quarter. And we will go also over some of the trends for training these large models. After completing this topic, what we will do next is looking into generative and interactive visual intelligence, where we will first start with self-supervised learning. Self-supervised learning is a branch of machine learning in which models learn to understand and represent data by getting some training signals from the data itself. We will cover this topic. It's one of the approaches that has enabled training of large-scale models using vast amounts of data that do not require labels, unlabeled data. And they have played a key role in recent breakthroughs in computer vision in general. And we will talk a little bit about generative models. They go beyond recognition. They actually generate. This is an example of the content of a Stanford campus photo, which is reimagined in the style of Van Gogh's Starry Night. This is known as style transfer, a classic application of neural generative techniques. Generative models can now translate language into images given a prompt. A model like DALL-E 2, generates an entirely novel image. This showcases how generative vision models blend understanding, creativity, and control in their generations. And you've probably heard recently about the topic of diffusion models in general. That's another thing that we'll be covering in this quarter. They basically learn to reverse a gradual noising process to generate images. And interestingly, in assignment 3, you will actually be implementing a generative model that generates emojis from text inputs from prompts, for example, a face with a cowboy hat, which is denoised from pure noise. Vision language models are the next topic of interest we will be covering. They connect text and images in a shared representation space, and given a caption or image, the model retrieves or generates its corresponding pair, as you can see. So there are a lot of advances in this area that we'll be covering some of the key examples. Again, this is a key task for cross-modal retrieval or understanding and visual question answering and so on. So we'll get to that in the class too. Moving beyond 2D, models can now reconstruct and generate 3D representations from images. And here you can see some voxel-based reconstructions, shape completion, and even 3D object detection from single view images. So 3D vision enables more especially grounded understanding, which is crucial for robotics and AR, VR applications. And finally, vision empowers embodied agents that act in the physical world. So these models often must perceive, plan, and execute, whether it's cleaning up a messy room or generalizing from human demonstrations. So with all of these, we will be covering different topics around generative and interactive visual intelligence. And finally, we will cover some human-centered applications and implications, and as Feifei very nicely explained. So there is computer vision and generally AI have been having a lot of impact in the past years, and it's very important to understand the human-centered aspects and applications. And some of these impacts are reflected by these awards that are going to researchers in this space. It was first recognized by the Turing Award 2018, which is the most prestigious technical award given to major contributions of lasting importance for computing. Jeffrey Hinton, Yoshua Bengio, and Yann LeCun received the award for conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. Beyond that, last year in 2024, Jeffrey Hinton was jointly awarded the Nobel Prize in Physics alongside John Hopfield for their foundational contributions to neural networks. And finally, I want to very briefly mention the learning objectives for this class will be formalizing computer vision applications into tasks. As you can see some of the details here. We want to develop and train vision models that operate on images and visual data, images, videos, and so on. Gain an understanding of where the field is and where it is headed. That's why we have some new topics also covered specifically in this year. So the 4 topics that I mentioned earlier, we will be going over the basics in the very first few weeks. Bear with us because these are important topics and you need to understand the details first, how to build the models from scratch, and then we'll get to more interesting, exciting topics of the day, computer vision. And finally, we will have one big lecture on human-centered AI and computer vision. I want to just leave you with what we will be covering next session. That's going to be image classification and linear classifiers, which will get us started with the world of CS231N. Thank you.